Maybe let's go back one or two slides, just because we have a little bit of interruption. Okay, now
This one.
Zentropy, yes. Yes, I think.
All right. So this is about Zentropy. How the Zentropy, the term came. Well, we know the entropy drives the system, so it's second law. Then Z is Zustandssumme, the German word. Some of the states is used for partition function. And as the Zentropy, the term started last year, was suggested by Josh Roberts in a seminar I gave. Exactly 1 year now, it was June last year. It's trying to really capture the total entropy of a system. If you look at the first publication was in 2008 about the method. So it's very, today if you go to DOE or go to any funding agency, get a fundamental physics. There's one problem is that the computation cannot predict reality. Okay? There's no computation can predict reality without fitting. Okay? So that's the problem. Because why is that? So what's the reason? I think the entropy solve that problem. Okay, then we solve that problem. So because the reason is because all the previous calculations cannot get all the total entropy, only partial entropy. So our must hope get all the entropy in place. So it goes the standard statistical mechanics. The partition function of a system is the summation of the partition function of the microstates of the system. The free energy F is the homogeneous energy. EK is the total energy of the individual microstates. And you can calculate the probability. That's how the probability is calculated. But you have to realize that Z is unknown. Z is the solution. Okay, you have to solve the whole equation, the minimization, the free energy to solve it. And then you can calculate the free energy of the system. And you can calculate the entropy of the system. So that's basically the standard statistical mechanics. And this equation is used in the literature. And we found a problem of this equation is that if you have a single state, you have one state of a system, then you find F equal to EK minus TSK. That's standard thermodynamics, but it's also equal to EK. That means SK equal to 0. SK equal to 0, it means it is a pure quantum state. The pure quantum is good. That's basically each electron is a state. But you have how many electrons you have, right? 10 to the 23rd power. Okay, so it's a huge number. That's why quantum mechanics cannot directly be used. It cannot directly be used. But still, we know it's building blocks, right? Electron is building blocks, atoms and electrons put together. But we cannot use it directly. Okay, so we have to understand more about the entropy. So that's what we learned about entropy change. If you add heat, develop a temperature for equilibrium system, then you add a mass into it, still equilibrium system, or you can do non-equilibrium system. As I mentioned, most textbooks talk about the first one, and I think the second one and the third one, except the last term DIP, second one is I think is only talking in my book. And that's very important because for open system, that's a very important one. And now we want to get the total entropy. You do experiments, you measure heat capacity, you get total experiment, the total entropy by integration. Okay. The heat capacity, C is heat capacity. Let me use this point. So now if you take the standard statistical mechanics I mentioned on the previous slide, you get a Boltzmann one, then you get a Gibbs one. Okay? You get Gibbs one is a revision of the Boltzmann equation. I still don't understand why we still teach Boltzmann equation. Let's equation should be abolished. Okay? Should teach Gibbs equation. When all the pK is the same, it reduces the Boltzmann equation. Okay, so that's just we should change it. Okay, anyway. Now, from quantum mechanics, we know that. Okay, you can calculate them from DFT. So DFT was invented in 1960s. That's just the time I was born, so it's the time too. So you calculate two important entropy. One is the entropy from electrons and the entropy from phonons. Okay. So that was what missing in the quantum in the statistical mechanics. So if we are familiar with the density functional theory, it's got DFT, that it calculates one thing. The theory is that for any system, it's a ground state at 0 Kelvin. So it has a unique electron density. That means you have a lot of electrons together. So it's a mixture of pure quantum states. So now immediately, if it's mixed with pure quantum state, you cannot use the standard statistical mechanics anymore. Okay? So these two are incompatible. compatible. So we know that if at T equals 0 Kelvin, entropy equals 0 as third law, even with ground state, or the mixture of two quantum states, but at final temperature is not equal to 0 anymore. You have two entropy contributions, the electron and the phonon. So in addition to ground state, you also non-ground states too. That means it's other states, which just go back to the statistical mechanics, you can have a probability of final temperature. So our Zentropy theory is basically put two together. We take this DFT phonon, DFT entropy, plus the statistical entropy. That's what we have. So this is called Zentropy. It's quantum plus statistical. So the red part is quantum, the blue part is statistical, and the green part is experiments. So now you can see now, right? Either part is not enough to produce the experiment data. So there's a huge effort in the DFT side and the red side. A lot of calculating, a lot of money put in there trying to predict the experiment data, the experiment property. You cannot do that because you're missing a big portion at the final temperature. Okay. And the quantum mechanics statistical mechanics cannot do that either because it assumes SK equals 0. Okay. So I have to put them together. So then we have a lot of examples to do that. It's basically the quantum plus statistical, give you some dynamics. Then we cannot define the material genome now. The new definition of material genome is a microstate from DFT. So that's the new definition of material genome. In my opinion, if you want to predict the materials property, you want to predict it, you have to take the microstate from DFT. You want to do the prediction. And if you do that one, you can really talk about the disorder and fluctuation of microstates. You can emergent properties. Emergent property means that if you individually study microstates, you will not get the properties. But if you put them together, they give some properties you don't have before. Like the negative sum expansion. That's one example there. So again, this example, if you compare these two equations, it's standard statistical mechanics. Okay, it's EK. If you use Zentropy, we call it Zentropy statistics. You get now entropy has one more term, right? And then your free energy is different. It's EK to FK. Then your partition function is different. It's equal to FK. Your probability is different. Now you see that the probability becomes very different. Okay. So that's where the free energy becomes very different. All the properties become very different. So actually, we can stop here now. That's Zentropy. But let me give you a graphical presentation what it means. So this is standard statistical mechanics. You have different microstates. You have a distribution of them. You calculate entropy. But however, each microstate, you could also have has entropy. So have to sum up together. That's basically the entropy concept. And then how do you get SI, SJ then? You do the quantum mechanics. So now get a quantum mechanics. You can go all the way go down to electrons, the pure quantum state, all the way up to whatever system you want. You can go to the black hole. Actually, we're working with black hole. I want to get a paper on black hole out, hopefully pretty soon, because I found that the black hole entropy by Hawking at Cambridge is missing one term. Okay, he only has the last term. He only has the quantum term. He didn't have the statistical term. So I think we should add statistical into his formula. So we have a lot of examples which we did, published since 2008. Magnetic materials, ferroelectric materials, semi-electric materials, and we are working on the quantum criticality, superconductivity, melting, black hole. I hope I have 1, 2, 3, 4 papers published in a year, which are on 4 different, completely different topics. Okay, so I hope my goal is to get in 1 year time, publish 4 papers on the 4 topics. So let's go back to the problem we talked about before, the negative sum expansion. So what it means is that basically now you have so many different microstates. Each of them is a magnetic spin configuration. We can calculate the probability from DFT. If you do that one, then you can think about how many states you need, right? So we take 9 ion items, so 2 to 9 power, you have 5 and 12 configurations. But in the symmetry, you reduce them to 37 of them, so you can look at each one of them. Let's give 4 examples here. You can calculate the energy, 0 Kelvin energy by DFT. So you find that the FM is the lowest energy state, the other ones are the high energy states, but they all have smaller volume. That's why they have negative substitution, because when temperature goes up, the metastable ones start to show probability, and as together, the total volume can decrease, even though each of them increase volume. So that's what the physics is behind it. So we can calculate those as free energy. Now, free energy is very interesting, right? If you look at the energy, free energy alone, there's no transition because the ferromagnetic state has all the lowest energy at all temperature. If you talk about free energy alone, there's no transition. However, the energy difference decreases divided by kBT. It's smaller at high temperature. You increase probability. What does it mean? That means at 0 Kelvin, 100% ferromagnet, but when temperature goes up, it becomes less than 50%, even though its energy is lowest. Okay? So that's so you have the energy given from the quantum mechanics, the probability from the statistical mechanics, put them together. Now we predict the magnetic magnetization. We predict the negative symbol expansion. Okay? Now you think you actually can do a lot of things to study it. You can calculate PD diagram. You can actually calculate pressure effect, or you can also part the volume effect as function for temperature. You can get the we call it the some extent divergence. Some extent becomes minus infinite. That's a critical point, and you can prove it from thermodynamics. It's a complete prediction without any experimental information. See, we have many examples that I mentioned in theorem, and again, theorem is different, right? Theorem is positive some expansion, so the divergence is positive. So we can put it positive and negative. But if you're familiar with one very interesting example, is negative, is positive. Okay, oh, this one big one, and this one is water phase diagram. We're going to work on water phase diagram. What is interesting? This one is negative, right? This one is so this was negative slope, so you get negative some expansion. That was positive, you have positive some expansion. So that's why water has negative some expansion, because this line is negative. So water has negative some expansion from below 4 degrees Celsius. Now we can explain why is it. We can predict it. We have a prediction on another paper. We can many magnetic materials, and this is superconducting materials. That's my next topic. It's I wanted to predict the superconductivity, but this is the base structure of superconductor. And the magnetic materials were done. Now I wanted to show one example is about the ferroelectric material. Ferroelectric materials is lead titanate. This is the most classical ferroelectric materials. The transition also is from tetrahedral cubic. But however, if you look at the structure itself, actually it's not a cubic at all. It's all tetragonal, because the microstates are tetragonal. Okay, so the red line is from our simulation, the blue line is from the high resolution experiments, the black line is from X-ray. So you see very different results. What does it mean? That means if you look at the big picture or fine picture, you get different results. So you really need to get the microstates correct. So I will show one movie here. Is that? Oh, looks like it doesn't move. Oh, I think it has two screen issue. It doesn't move. Anyway, it has moving there. So what it means is the cubic itself, cubic structure itself is just because of fluctuation.
You can get a laser pointer. Maybe if you switch it to normal.
Oh, so we need one, huh? Okay, let's see. Switch off the laser one, it may cancel it, right? I cannot see what the mark is now.
That's the quantum chaos.
The quantum up, you see now here? No, here it is. No, it is, right?
Oh yeah, there, yes. Can you click?
I should click this one. Next one, point option.
No.
They should turn off the laser pointer. Yeah, go down the point option and the automatic. But visible is okay too. Yeah, right?
I don't know. How do we go back?
Is the laser pointer this one? No, it's going to move
Oh,
here.
yes.
Okay, so this one tells you that the white square is cubic, but the internal structure is not cubic. You see the blue item is titanium, it actually moves all the time. That's what we call fluctuation. I don't know whether you remember the last year's Nobel Prize, the one got from Greek. It's got a disorder of fluctuation going from atomic scale to planetary scale. So this fluctuation piece actually dictates all the properties of the system. Yeah. So we can do that from the simulation. We can actually figure out that the transition here, the red one, you see, what does it track like this, right? It flips like that, flips like that. So it changes all directions. Overall, it looks like cubic. But look locally, it's all tetragonal. So that really shows this micro states, the importance. But if you do the quantum state, you will not be able to do that because you cannot sample all the states. So then we can predict it, and so then we started to predict last year. We take the two type of domain walls, one's 180 degree and 90 degree. We put them together, we predict transition temperature. It's amazingly close to the experiment. It's 10 degree off. Okay. And the new paper is under review now for publications. So I want to close my talk by telling you that we need a data and tool. A couple of years ago, I realized that I need a new name. I like the name for this approach. We call the ocean of data. You see that inside that ocean of data. So it's this ecosystem. So it's called ecosystem. Here we have data generation, we have data processing, then we have data training. Okay? Then we go this cycle and together to continue generate the tools. The tools are developed by our group in order to, as I mentioned during today's meeting, in order to maintain this development, we created the nonprofit foundation to do that. So now we have regular training courses, and we start charging people now so we can sustain our activity. All right, I want to summarize the talk here. I hope I introduced the Zentropy concept to you. It really combines the quantum and the statistical mechanics. Okay. And the two communities, they're not integrated together. I think this one integrated together, so you can really predict the properties which we could not predict before. And we demonstrated for the different applications. I just get a new grant from DOE to extend this further for different properties. Well, if anybody interested, we are applying this to a wide range of materials now, complex systems. As I mentioned, that we're doing the quantum entanglement, that's quantum criticality, and I think the chance that metamaterials can be involved in something. Biosystems. I'm going to have a meeting when I get back to Cambridge. We'll talk with the bioscientists and see how the protein folding. Protein folding basically entropy. Okay, I'm going to predict that. I had a friend working in the forest, but the other one's country, continue, I don't know, but I know that I'm working with black hole. All right, I want to thank you. Sorry that the voice, the microphone was not on for a few slides. But otherwise, I'm excited that for this new approach can really predict the property we cannot predict before. Thank you. Thank you.
Thank you for weathering the heat, the technical glitches. So maybe let's have a short discussion now. I wonder if there are any questions from the mostly online audience. I'm looking at the chat window. So guys, feel free to ask any questions. I know it was a fast-paced discussion. Because personally, I have a couple of questions myself. So first thing that I was wondering is the quantum space, the additional term that you added. How do you do the actual computations of this summation of the quantum? Is it like a software tool that you developed, or
for the quantum one, right?
The red integral, yes.
The first one is basically you need to sample the red one, right? The red one. The red one is that you need to by sample internal degree of freedom. So if you sample all the internal degrees of freedom, then you will get all the states. Then you calculate the energy from the use commercial code or open source code. There are a lot of them, like more than a dozen.
And do you assume that there is like a uniform distribution of the states in your material?
Each microstate is uniform.
So there is no like that one state is more common than the other?
It is. The probability change, right? As the probability, the PK changes. So if you go to 0 Kelvin, the ground state is 100%. And when temperature goes up, it decreases, and then decreases even further.
And how can we compute those probabilities of those states?
So that's the second equation you have here. So that's what you calculate like this. The last equation, the PK equals ZK divided by Z. So it's the difference between the two PKs, right, left and right. You immediately see that the left and right underestimate the PK. Because EK is FK is equal to EK minus TSK. So this was much more accurate. A different value you can do that. Depends on the value of SK, how big it is.
Can I just clarify your notation? So E is internal energy.
That's right.
And F is Gibbs.
It's a Helmholtz energy. Helmholtz energy. But if you use temperature and pressure, would it be the Gibbs energy? So it's a free energy. This is for the canonical system. So it's Helmholtz energy. But it's the first time I used Zentropy statistical mechanics. Yeah, I want to differentiate that one too.
Yes. So when you calculate the probability of those different states and you feed it in,
then you go back, calculate the energy, right? Calculate the entropy. Then you can calculate all properties.
But you said you do not need any calibration, right?
No calibration.
So you start from the atomic structure.
That's right.
From the states.
Yeah. So what you do is that you calculate the FK basically. You
calculate FK.
Let's use DFT, density function theory. You have three terms. You have the FK has three terms. One has the internal energy, then have the electronic contribution, the photon contribution. So that's in this this equation we have here. You have three terms. It's back here. So you have three terms from the this one. Okay. So you see, you have two entropy here, right? The quantum mechanics. You calculate the entropy from electrons, entropy from phonons. That's two. Then you have calculate total energy. The three terms that together give you the FK. It's completely predictive.
So basically, I'm saying that we can quantify those basic building blocks.
That's right.
Almost like quantum level.
Exactly.
And once we measure those, it's like a menu catalog of those.
Yeah.
Then we can go ground up.
Exactly.
And predict all kinds of phenomena.
All properties so far.
Without fudging or calibrating.
No calibrations. The only thing is that you got to make sure you have enough. You capture all the macro states, right? So that way you can based on your computer, you can do as many as you want, but sometimes you don't need it all. That's the statistic comes in.
I see.
Yeah.
So you need to make sure you can generate all the states and you can find them. Yes.
Yeah, enough.
So when you generate 500 states and then reduce it to 37,
yeah.
how do you go about doing that?
Well, that's one symmetry. You can do symmetry analysis, you have another code. You can do symmetry, 502 of them. You can symmetry analysis, say you are only 37. And ones are multiplicity. Yeah.
I want to congratulate you. Yes, I think this seems like a big breakthrough. Yes.
I'm so excited. I tell you, unbelievable. When we figured out. We did calculate before, but we really did not fully understand the fundamentals behind why it works, right? What was the main thing? So when we figured out this scheme, that's the true one. So then we predicted so many things. Right? This is everything, so to speak. All the experimental measurements.
Yes, because sometimes we don't ask ourselves questions about basics. And yeah. I was thinking about two things, like how to visualize those things. I attended a conference last week and there was very nice visualization of like chemical kind of packing of atoms and where they end up, that you need to pack something inside a tetrahedral block or where it ends up. oftentimes we look at the notation like symbolic letters, some kind of lines, but we don't visualize it. I was thinking this was striking for me that, especially for new generations of students, we need to be better at visualizing, like this animation which you showed with,
This one actually,
oscillations.
this
Yes.
is very similar to what you mentioned. In that demonstration, you move the atoms, right?
Yes, and
or
sometimes
atom
you pack
clusters.
them in between.
But here we packed all the macro states in 3-dimension space.
Yes.
You basically pack all the 3-dimension space in all this. But see, you start with one macro state, right? But the next one you have probability. You have 512 probability. Right? So you really don't know which one would be. It's all statistics. So if you look at the whole sample, if you pack all of them together, it looks cubic. But actually, individual is not cubic.
And I guess this is just my personal curiosity, because you seem to have very good intuition. So when we go to the small scales, what are the driving forces that keep the structures?
Entropy.
Yes, but I'm always confused about electrical and magnetic forces.
Ah.
Like, what are the fundamental forces? Like the Lagrange, it's gravity. We can't reconcile it. Like, what are these forces? Like electrons, negative, positive. What is magnetism in all this? Like, what is the interaction? What is your intuition about this fundamental?
That's actually the electrons. It's all by electrons.
So everything is done by electrons, but where is the magnetic field coming from?
Oh, magnetic field. Oh, that's a very interesting question. That's extremely. I had the same problem before. Well, what does really magnetic mean? Right?
Yes.
It's actually just the electron distribution. It's the boundary formation. Okay. When the boundary is isotropic, they don't have magnetism. It is when the boundary lines up. You get spin origin. Spin is basically the origin of spins, right? The spins in origin is actually electron origin.
Because that's what I thought, that they all spin in the same direction.
It's all electrons.
As they pass on the energy.
Yeah. So it's all electron origin. You can plot it. You can plot the electron distribution. You can see the spin line up.
But I guess then we can become even more philosophical that light is a magnetic wave.
Yeah.
And apparently it transfers in vacuum. There are no electrons there. How is it possible that we have those waves?
That's a very interesting question, right? So what is in vacuum?
No electrons, no nothing, you would say, right?
Well,
is that true?
It got to be something, right? It got to be something, right? Well, vibration has to transfer. You have to have vibration. What's going to vibrate? Something's going to vibrate.
Yes, I think that was this dilemma of ether, but now we have dark matter. Nobody can find it, yes.
So it's the structure of space. Right? That's the next question. What is the structure of space?
Yeah, I think that's what is interesting about this. Because if you think about electron, you think about the particle, right? You think about the particles, right? Electron and particle. But the quantum, you have this wave function, right? Wave. They have wave property too. So it's wave the particle combined together. So I don't understand. I don't fully.
Yeah, this is to me is a paradox. I can't digest it.
But that was from the. You think about this one, right? Between two electrons, how do they interact with each other? There's nothing in between. But
they do interact. Yes.
Yeah, that's wave. They have the wave here, right? It's here. Yeah, if you shrink yourself to electron, between electrons are vacuum. There's nothing between electrons. Just like in the vacuum, you say it's vacuum, nothing there, but it's something there, right?
Yes.
That's what between electrons. What are between electrons? Vacuum, nothing. But that's what the field, the wave. You have the wave there. The reason is because it's actually because of quantum mechanics, because of probability. So the electrons everywhere is nowhere, right? It's a probability there. So the space is a field and probability. That's what I want to say. It's a probability. So it's not really you cannot measure electron, the position and velocity at the same time. We know that. Right? So as soon as you measure it, you fix it. You disturb it, right? So then you really think about the FT. It's very funny. The FT is not an individual electrons because they cannot solve it. So they say I have a density, the probability. Density is basically the probability.
Almost like things dissolve. Yes, but in kind of field Matter, yes.
You feel it. That's right. It's really the feeling. It's a field. It's a field of the, between the electrons. So that means the vacuum have a field. That's like between two electrons.
Yes, and then it seems we cannot explain the fundamental things like triboelectricity. I was told last week that we all have seen things like, when you wrap some materials, you create electrostatic charge, and the hands will raise. Nobody fully knows why this is happening. This kind of transfer of electrons between some materials.
They must have electron transfer, right?
Yes, but why this material to that and not the other way around? Yes, and
that's the density function theory can solve that problem. Yeah, it actually solve it. You could, because you can calculate how the electron distribution changes as your mechanical force, or you put an electric field or magnetic field. The electron density changes. So the DFT, in my opinion, DFT that's the last equation here. Okay. Because it's really that you mentioned this one, it's really this equation.
Yes.
Okay. So you can have no atom motion. So this is the atom motion, it's the second equation. But first is the electron distribution. So this distribution, like a single superconductor, this distribution is affected by anything you do. You get mechanical force, you get electric force, you get magnetic force, that distribution will change. So that's why, of course, if you say what affects the electron, that's quantum mechanics cannot do anymore. You have the nuclear physics to answer that question, right? But the electron level, that is actually the Fermi-Dirac equation governs it.
So it's used different formations will have different fields. There's a question from the online audience from Chung. Hi, from Sally. So Chung, do you want to unmute yourself and just ask the question here? I'll try to.
Oh, should be here. Should I hear it or you hear?
Can you say
Okay. Thank you, Stefan. Thank you, Professor Liu, for the very inspiring talk. I personally work on DFT and molecular dynamics simulations, and I'm now become very interested in simulating the solid liquid interface, where there are reactions happening. And I understand from your talk, you did a lot of work on probably the bulk solid material, yeah?
Yeah, mostly our results are solid phases. That's right.
Okay, yeah. Have you thought about this the interface problem? I haven't. Yeah, I'm thinking to do some work, but not a very clear idea yet, because the solid material, the design of this will depend on how the solid material interact with liquid, and so not only on the solid material property itself, but also the interaction between the at the interface, what kind of product it produced. I'm talking about the electrified system in batteries, for example, in fuel cells, in batteries where you have, for example, a metal anode, and you have a liquid electrolyte system, and then you may want to design some metal to provide provide some property, but then its interaction with the liquid electrolyte is also important, because that will determine, we want to have, for example, stable system. So that I think that become more complicated.
That's right. That's right. But there are people doing that, right? The one approach which you can do is I don't know, maybe a firm called AMD, AB initial molecular simulation.
Yeah.
That one, in my opinion, if you want to start liquid, that's probably the best approach. But of course, it was solid is very hard for the AMD simulations, right?
Yeah.
If you're you're not talking about melting, just about the solid liquid interface interactions. I think that one's probably the best way to do it.
But if I want to design a metal, for example, if I want to design an alloy, and I want to that could be different composition for the alloy, and then which alloy would be better in interacting with liquid electrolyte. That actually involves huge amount of simulations.
Yeah, that's right. So that's actually a very hard problem. The reason because the liquid and solid have very different time scale in terms of evolution, right? So you have to fix this and it simulate the liquid, and then see the surface relaxation. Then you can see a lot of the formation of phases on the surface too. Yeah, that's very hard. In principle, well, if you think about my Zentropy approach, then you basically the idea would be you do all kinds of microstates configurations. Then you put it back together, predict the property.
Okay.
I think, but we are now working on one, the melting. We're working on melting now. So we want to use the Zentropy to predict the melting. At the moment, people do AMD simulations, which is not very accurate. People do AMD simulations is limited by size and also very expensive in terms of computing. We are now using Zentropy to predict the melting temperature. I hope we can write a paper very soon for use Zentropy to predict the melting. Yeah. So I think.
I think your approach is very inspiring. I will think about it.
Okay. So if you have
thank you for your advice.
Any practical questions, let me know. We can work on that.
Yeah, sure.
So it's
exciting.
I found so many good interactions since I came to Cambridge, UK.
Yeah. Yes, Cambridge is a good host. Yes.
It's very nice.
Very nice. Are there any more online questions? Let me check. If no more questions, then maybe we can finish the official part of the seminar with a round of applause.
Thank you. Thank you.
That's a virtual applause.